Yes, good morning, my dear friends, and welcome to physics online classes. Look here, in the previous class, we are discussing so important concept that is about construction of PN junction, and also we discuss about the formation of depression here, and also discuss about the barrier potential. And in the today's class, we are going for the lecture number 7. We are going for the lecture number 7, and we are going for the what is the effect of the after applying the external voltage or after applying the battery. What is the effect of the applied voltage or battery to the diode? We go for that, and before that, as usual, we go for the revise. You can recap what you studied in the last class. Look here, as I said in the last class, if you take the individual p-type semiconductor, it is no use. It means you are having very less applications, because the p-type semiconductor, it is a electrically neutral. Similarly, for n-type semiconductor, if you take individual, that also electrically neutral. You are not having any more applications, more uses. Then what we'll do? We'll combine the p-type and n semiconductor. There are so many advantages. As I said here, in electronics or in physics, whatever constructing the devices, it may be your amplifier, it may be oscillator, or maybe your rectifier, all are having one or two PN junction inside of the device or circuit. Example, to take the transistor. Basically, transistor is a three-terminal semiconductor device. But inside the transistor are the two junctions. Inside the transistor are the two PN junctions. Like that, they are having so many. Consider any electronic gadgets. Inside that gadget, you are having one or two PN junctions inside. It means it is the heart of the semiconductor devices. The PN junction is the heart of the semiconductor devices. And as I said in the last class, if we join mechanically a p-type semiconductor and n-type semiconductor, that is not good. That is not correct. Take one small piece of p-type semiconductor, take another one n-type semiconductor, then join mechanically is not correct. You have to use some special techniques. You have to use some special process. By that method, you have to combine or you have to join the p-type semiconductor and n-type semiconductor. Combine or join the p-type and n-type semiconductor by this special techniques, by some special process. You can join or you combine the p-type and n-type semiconductor. And as I said in the last class about if you consider the PN junction. Consider the PN junction. In this PN junction, the important thing is about, as I said already, if you take a small piece of semiconductor, it may be your silicon or germanium. Take a small piece of semiconductor, it may be silicon or germanium. Next, what you have to do? By adding 1/2 portion of the traveling impedance. And by adding another portion of the pent-out impedance. And separating the p-type and material is something called PN junction. Separating the p-type and material junction. That is something called PN junction. It is simple way of construction of PN junction. Another is there. Another is what are they? You take a p-type semiconductor and diffuse a n-type semiconductor on the p-type semiconductor. Take a p-type semiconductor or you take a silicon germanium by diffusing one side with the p-type semiconductor and by diffusing another with the n-type semiconductor. That is also another one method. It means first you take your silicon or germanium one piece of semiconductor, you take a pure semiconductor or germanium, then what you have to do? By diffusing one side with the p-type semiconductor, by diffusing the another with the n-type semiconductor, and this is also another, with the process of diffusion we can construct the p-n junction. And similar, very simple is about by adding one side of the trivalent impurities, by adding another the pentavalent impurities. Or I said also by adding one side of the acceptors, by adding another side of the donors. Separating these two material junction, separating the p-type antimaterial nothing but junction, separating the p-type and antimaterial junction. That is nothing but your p-n junction. And important thing in the p-n junction is about the formation of depression layer. This is so important. The formation of depression layer. It is so important. The formation of depression layer. Depression layer. This is so important. We can see in the last class. Once again, repeat that. The formation of depression layer. Look here, take a small piece of it, as I said here, take a small piece of semiconductor, and as I said here, in the one side you have the, consider it like that. This is your p-type semiconductor, this is your n-type semiconductor, and as I said here, in the p-type semiconductor having the holes are the magnetic areas. In the p-type semiconductor, the holes are the magnetic areas. It means the holes are more as compared to the electrons. The holes are more here. No doubt you are having the electrons also there, but they are magnetic areas. The number is very less as compared to the holes. The number of electrons will be less, and also having the negative immobile ions. They are called negative acceptor ions. They are having the negative acceptor ions. They are having the negative acceptor ions. Because as I said here, whenever you are adding the impurity, especially if you are going for the p-type, you are adding the impurity, trivalent, it may be your boron or aluminum, that added impurity that acts as a immobile ion, that acts as a negative immobile ion. That also called a acceptor ion. That also called a acceptor ion. That is having the negative charge. That is immobile because it is not moving, and it is also no use for the conduction of current. It is totally bound to the nucleus. That is about the negative immobile ions. And similarly, in the n-type semiconductor, as usual, we are having the electrons are more. The number of electrons are more in the n-type semiconductor, and here also the holes are less, but because they are magnetic areas. In your n-type semiconductor, holes are magnetic areas. And here also the positive ions. They are called donor ions. Positive donor ions. They are in the positive donor ions, because whenever adding the pentavalent impurity, that added impurity that acts as a positive ion, and as I said already in the last class, we are studying about the two types of current. One is called diffusion, and second one is drain. It means actually what is called diffusion current. What is called the diffusion current? Nothing but what is called diffusion current and what is called the depth current. Look here, as I said, the p-type semiconductor, the holes are the magnetic areas. It means holes are very more here. And here in the n-type semiconductor, the electrons are very more, and there are the magnetic areas. And look here, actually what happens here, because of the concentration of holes is very more here, and concentration of holes is very less here, and concentration of electrons is very more here, and concentration of electrons is very less here. It means because this concentration difference, because of this constant gradient, what happens? The holes, they will diffuse from p to n side, and the electrons, they will diffuse to n to p side. This moving of the electron holes, or this diffusion of electron holes, they will get some current. That current nothing but the diffusion current. That current nothing but the diffusion current. It means in the p-type semiconductor you are having the holes. In the n-type semiconductor you are having the electrons. No doubt, because of the concentration gradient, because of concentration difference, what happens? The electron they move towards the p side, and holes they move towards the n side. This diffusion of electrons and holes nothing but the diffusion current. This is nothing but the diffusion current. Look here, in the important thing, the diffusion current, the electrons are moving in the electrons and holes are moving in a particular direction. They are having the definite direction. They are having the definite direction. That is nothing but your diffusion current. And another important thing, whenever the electrons are diffused, actually what happens? Some of the holes, whenever they are diffusing towards the n side, what they will do? They will recombine the electron. Some of the holes, while diffusing towards the n side, they will recombine the electron. In the same way, in the n-type semiconductor, the electrons, whenever they are diffusing the p side, this electron will recombine in the hole in the p side. Whenever they are moving, electrons are moving from n to p, holes are moving from p to n. In the same time, what happens? Some of the electrons they will recombine with the holes in the p side. Also, some of the holes they will recombine in the electron in the n side. And actually, no doubt, you are having some layer. In this layer, you are not having any charge carriers, because electron hole recombine, they will create a neutral, they will become the neutral, they will disappear. Whenever electron will recombine, they will disappear, they will neutralize, and they will having some layer. In this layer, you are not having any charge carriers. That's what is called depression layer. It's called depression layer. And important thing here, no doubt, electrons are here, the holes are moving. Here electrons are moving. What about this positive donor ions? What about negative donor, negative acceptor ions? They will forming one layer. They will form a layer. The donor and acceptor ions, they will form a layer. That layer nothing but the depression layer. This is nothing but the depression layer. That is nothing but your depression layer. Depression layer. It means whenever the hole they will diffuse towards the n side, they will recombine, they will be neutralized, they will disappear, and you are having some space. In this space, you are not having any charge carriers. And also, the electron, when they move towards the p side, they will be recombine the hole and neutralized. And important thing, here they will create some region, some area. In this area, what happens? You are not having any charge carriers. And what about this uncompensated negative ions from the p side and uncompensated positive ions n side? They will create this layer. That layer nothing but the depression layer. Why it is the depression layer? Because in this layer, you are not having any electrons or holes. In this area, you are not having any electrons or holes. Only you are having there is called immobile ions. In the depression layer, you are having the positive and negative. They are immobile ions. Immobile ions. They are immobile ions. It means they are not moving. They are also not taking place in the conduction of the current. This means the layer that is having negative and positive ions, this layer will be the depression layer. In this layer, we are not having any charge carriers, and it is also called as space charge region. It is also called as space charge region. It is also called as right here space charge region. Space charge region. It is also called as space charge region. Another name of depression layer is also called as space charge region. And what is the importance of depression layer? Once the depression layer forms, what happens? They will oppose the further diffusion of electrons holes, because these holes they will be repelled with the positive ions. These electrons they will repelled with the negative ions. That's why they are not moving from n to p or p to n. It means before formation of the depression layer, no doubt the holes will diffuse towards the n side and electrons will diffuse towards the p side. Once the depression forms, then what happens? The electrons and holes, their diffusion process stops. or reduces. This is about the importance of your depression here. It is also called as space charge region. In this region, you are not having any electrons, you are not having any holes, and it is having only the immovable ions. You are having the negative acceptor ions and positive donor ions. Right? And important thing about in this area, whenever you combine the P and semiconductor, you are having the diffusion current. Because of diffusion, what happens? Some of the electrons will recombine, they will disappear, they will neutralize, they will create some layer. In this layer, the uncompensated, your negative ions from C side and positive ions from the N side, they will create a layer. That layer is called the depression layer. Right? And also, what is called barrier potential? What is called the barrier potential? What is called the barrier potential? What is called the barrier potential? What is called barrier potential? Here, this negative ions and positive ions, they will create some electric field, or they will create some potential difference. They will create some potential difference. That potential difference is nothing but the barrier potential. It is nothing but VB. It means here, what I said here, this negative ions and this positive ion, they will create some electric field. They will create some potential difference. That potential difference, that electric field, nothing but your barrier potential. Right? This negative ions and positive ions, they will create some electric field. They are having some potential difference. That potential difference, nothing but barrier potential, we can write as VB. The VB nothing but the barrier potential. The VB nothing but the barrier potential. And as usual, the barrier potential of germanium, that is your 0.3, and for your silica, that is 0.7 volts. I am saying about the barrier potential about your germanium. If you are in germanium drive, that is short conducting up to 0.3. If you are using the semiconductor, that is short conductor 0.7. That is nothing but the barrier potential of your germanium and barrier potential of silicon. The barrier potential nothing but the negative ions and positive ions, they are having some potential, they are having some electric field, that electric field, that potential nothing but barrier potential. Right? And finally, as I said here, important thing about what is called drift current. Drift current nothing but the current, it is nothing but in semiconductor current because of electrons and holes. Here, this the current because of this barrier potential. Because it's barrier potential, what happens in the N type, the holes are magnetic. These holes they move. In the P type, in the N type, the holes are the magnetic. They are moving. In the P type, electrons are moving because of this VB, because of this barrier potential. That movement of electron holes because of this VB, nothing but drift current. The drift current nothing but the moving of electron holes because of this barrier potential, because of the electric field. That is nothing but drift current. Diffusion current, it is because of concentration gradient. Drift current, that is because of the barrier potential. It means what are the minority carriers in the anti-semiconductor, what are the minority carriers in the P-type semiconductor, they will move. That movement of holes and current, holes and electrons, they will the drift current. This is about the importance about the depression layer and formation of the barrier potential. Now we go for yesterday we discussed already what is called the biasing and types of biasing. Maybe I said already. Now we go for biasing. Nothing but biasing. Biasing nothing but applying the external voltage or by giving the battery connection to the diode, nothing but biasing. Applying the external voltage or by giving the battery connection to the diode, nothing but biasing. But there are two types of biasing. One is called forward bias, and second one is reverse bias. reverse bias. And as usual, yesterday discussed, this is the symbol of your diode. This is the symbol of your diode. And here important thing, why it is called diode? It is called diode. Nothing but di nothing but two. Body nothing electrodes. It is having the two electrodes. It is having the two electrodes. It is nothing but the two electrodes. The symbol of the diode. And important thing, the diode is a two-terminal semiconductor device. What is diode? It is a two-terminal semiconductor device. It is a two-terminal semiconductor device. Why it is called diode? Di nothing but two, body nothing electrodes. It is having the two electrodes. That's why I said diode is a two-terminal semiconductor device. And in this diode, if you apply the extra voltage or if you apply the battery connection, to the diode, that is nothing but biasing. How you are applying the battery connection? That is nothing but you are. Now, what is forward bias? The forward bias is but the P-type semiconductor is connected to the positive of the battery, and N-type semiconductor is connected to the negative battery. That is nothing but forward bias. Forward bias is nothing but the P-type semiconductor is connected to the positive battery, N-type semiconductor is connected to the negative battery. It means same positive, negative, negative, same polarity. That is nothing but forward bias. And the reverse bias. What is the reverse bias? Nothing but same diode. If we change the polarity of the battery, or you can change the polarity of the diode also. This is nothing but your reverse bias. This is nothing but your reverse bias. In reverse bias, what happens? Positive diode, negative battery. Negative. It means the P-type semiconductor is connected to the negative battery. N-type semiconductor connected to the positive battery. That is nothing but reverse bias. It means here opposite polarity. Positive, negative, negative, positive. Here positive, negative, positive. It means same polarity. Forward bias, opposite polarity, reverse bias. This is about the forward bias and reverse bias. It means you are giving more importance to forward bias. Actually, what is the most important property of diodes? Why you are giving more importance to diode? Because in the diode, the current conduct in only one direction. In the diode, the current conduct in only one direction. In the diode, what happens? The current conduct in only one direction. Or you can say it only works for only forward bias. It conducts only the forward bias. It conducts only the forward bias. It is also called as unidirectional device. It is also called as unidirectional device. It is also called as unidirectional device. Most important thing, in the diode, the current conduct is only one direction. In the diode, the current conduct take place only one direction. In the diode, the current conduct and take place only one direction. Or it works only in the forward bias. It conducts only in the forward bias. Or it is also called as unidirectional device. This is about the important function of the diode. Now we go for most important thing. What is the effect of the forward bias to the diode? If you apply the battery to the diode or to the PN junction, what is the effect? If you apply the battery or if you apply the external voltage to the diode, what is the effect? We go further. It is so important for my question. Explain the working of the diode in the forward bias, or explain the PN junction if it is the forward bias or if it is the reverse bias. Now we go for the forward bias diode. We go for the PN junction. PN junction in forward bias. In forward bias. In forward bias. Look here. Now we draw the very big diagram. Now understand very easily over here. First, as usual, we have to construct a PN junction, and look here in this PN junction. As you know, connect here P type, connect here N type, And here, as usual, we consider the holes here, and also, as usual, you know, the holes are there carriers. Also, we are having the electrons. I am not considering the ions because there is some confusion here. If you consider ions, there is confusion. Only consider about the electron and hole. And here, we are having the electrons are the carriers. No doubt. It means the more number of electrons here and less number of holes are there. And the important thing here also not considered the positive ions. Here also not considered the positive ions. If you consider some confusion on that, right? And as usual, we are having a depression here because of the diffusion of the electron holes. We know already they will create a depression here, and also having a barrier potential. That is nothing but the VB. And now, if you apply the external voltage, to the diode, especially that is nothing but forward bias. Yes, it is nothing but VI. Look here, this is the diagram of your forward bias, P injection in the forward bias. Look here, first you write what is forward bias. You write here what is the forward bias. Look here, the forward bias nothing but first step what you write. What you write? The forward bias nothing but the positive of the look here, the first step what you do, the forward bias nothing but the P-type semiconductor is connected to the positive battery and N-type semiconductor is connected to the negative battery. This is first step you write. What is forward bias? The P-type semiconductor is connected to the positive battery and N-type semiconductor is connected to the negative battery. First step you write what is forward bias. Done. Second step. What you write second step? In the second step, look here in the P-type, the holes are the magnetic areas, and as you know, holes are in the positive charge. And in the N-type semiconductor, electrons are the magnetic area, they are having a negative charge. Actually, here what happens? This hole will be repelled by the positive battery. This hole will be repelled by the positive battery, and also electrons will be repelled by the negative battery. It means what? The holes will be repelled by the positive battery, and electrons will be repelled by the negative battery. Because this what happens? No doubt, the holes and electrons they will move towards the junction. Because of the hole will be repelled by the positive battery, electron will be repelled by the negative battery. It means what happens? The holes they move towards the junction, electrons also they move towards the junction. Because of the applied voltage. Because applied voltage what happens? The holes and electrons they will be moved towards the junction. When they move towards the junction, then what happens? They will reduce the depression layer. Because of the electrons and holes, they will be moving. They are moving from the it means in your if you apply the forward voltage, because this voltage what happens? The holes will be repelled by the positive battery and electrons will be repelled by the negative battery. They move towards the junction. And when they move towards the junction, what happens? They will reduce the depression layer. Because the hole are moving this side, electron moving this side, they will reduce the depression layer. Because of the electron and hole, they will move towards the junction. If they are moving towards the junction, what happens? The depression layer will be reduces. We are decreasing the width of depression layer. Because of the electrons and holes will be moving towards the junction. This is one important reason why the diode conducts only in the forward bias. Because in the forward bias, the depression layer is very narrow. The depression layer will reduces. Why the depression layer reduces? Because electrons and holes they will move towards the junction. In the depression layer, in the forward bias, what you want to write? in the forward bias, the depletion layer, in the forward bias, the depletion layer decreases. Because of the depletion layer increases, what happens? The electrons and holes, they move easily from the N to P, P to N. If the, as I said, if the depletion layer is very more, the electrons and holes, they are not moving. It means because of the forward bias, because of the holes will be repelled by the positive battery, electron repelled by the negative battery. It means holes and electron, they move towards the junction, they will reduce the depletion layer. The depletion layer decreases. You are reducing the depletion layer. And if the depletion layer reduces, no doubt electrons are and holes are moving, will get the current. Important thing, keep it in mind, in the forward bias, the current is because of majority carriers. The current is because of majority carriers. Because as I said, here electrons majority carriers, here holes are majority carriers. It means here electrons are moving, the holes are moving. It means in the forward bias, the current is because of majority carriers. The importance is current is because of majority carriers. Majority charge carriers. It means in the forward bias, the current is because of majority carriers. Yes, the electron majority carrier type and holes are majority carriers in the p type. It means another one reason I show you. This is very simple reason why the diode conducts only in forward bias. Very simple, because you are applying the external voltage. Because this external voltage, what happens? The holes will be repelled by the positive battery, electrons will repel the negative battery. They move towards the junction. They will reduce the depletion layer. This is very simple reason about the forward bias. Because of the you are reducing the depletion layer, then what happens? The electrons and holes, they will move very easily. And you get the more current in the forward bias. You get more current in the forward bias. That is regarded in terms of milliamperes. The current is in terms of milliamperes. Right. Another one is, look here important thing. Your what about the barrier potential? What is the effect of barrier potential? Look here is barrier potential and VI. What happens? They are opposite direction. Minus plus, plus minus. Minus plus, plus minus. It means what? Our applied voltage opposes the barrier potential. Applied voltage opposes the barrier potential. That's why also in the more current, they move from P to N and to P. Another reason is about the applied voltage will be opposite of the barrier potential, or the applied voltage opposes the barrier potential. Applied voltage opposes the barrier potential. That's why the electrons and holes are moving very easily. And as you know, if you apply, if you consider the germanium, and that is 0.3 volt, and if you consider the silicon, you are applying the 0.7 volt. It means if you have to apply some voltage, that voltage should be more than 0.7 and that should be more than 0.3. Then only your electrons, they will diffuse from N to P, P to N. You have to go through this barrier potential. As we know, the 0.3 for germanium barrier potential and 0.7 for the silicon. It means you have to apply the voltage that should be more than this barrier potential. Then only the barrier potential vanishes and current will move very easily from P to N to P. It means we have to apply the voltage. That voltage should be more than barrier potential. We have to apply the external voltage. That external voltage should be more than the barrier potential. Then only the electrons and holes, they will move very easily and get the more current. It means 2-3 things are important here. First, very simple point. What is forward bias? The forward bias is nothing but the P-type semiconductor is connected to the positive battery and N-type semiconductor is connected to the negative battery. First step. Second step, what about right? The holes are majority carriers in the P side, electrons are majority carriers N side. Actually, the holes will be repelled by the positive battery, the electrons will be repelled by the negative battery. If the holes and electrons are repelled by the battery, then how they are moving? The holes will move towards the junction, electrons will also they move towards the junction. The holes will move towards the junction, electrons also they move towards the junction. If the electrons suppose they are moving towards the junction, what they will do? They will reduce the width of the depression layer. They will reduce the width of the depression layer. They will reduce the depression layer width. They will reduce the depression layer width. And that's why they are having the more current that flow from the P to N and to P. Right? It means because of the you are reducing the depression layer, then what happens? You are having the more current in the forward bias. This is one reason. Another reason, what I said, your applied voltage and barrier potential, they are in the opposite direction. Your applied voltage and barrier potential, they are in the opposite direction. That's what happens. Your actually the total voltage V is equal to Vi minus Vb. It means our applied voltage will be opposite the barrier potential. Our applied voltage will be opposite the barrier potential. That's why also we are having the more current that flow from the P to N and to P. It means the applied voltage opposes the barrier potential. Because you see plus minus, minus plus. It means the Vi and Vb, they are in the opposite direction. And last point is about we have to apply the external voltage. That voltage should be more than the barrier potential. The barrier potential for germanium 0.3 volts and barrier potential for silicon, that is 0.7 volts. It means we have to apply the external voltage that should be more than the 0.3 or 0.7. Then only you are having the current start conducting. It means if you apply the more than this 0.3, 0.7, then what happens? This depression layer vanishes. The depression layer reduces, or it is very narrow, it vanishes. Then you are in the more current that flow from the P to N and to P. This is about in simple way of your understanding about the forward bias. Actually, another to go in deep, one simple thing is that whenever these electrons they move towards the P side, what happens? This electron they will recombine with the hole. Whenever the electron they move towards the P side, what happens? This electron they will recombine with the hole, the P side. The same time, what happens? Whenever the electron will recombine, what happens? They will break the covalent bond. Whenever the electron will recombine, they will generate some energy. They will generate some energy. Because of the recombination electron hole, they will give some energy. Because of that energy, once again it will break the covalent bonds. Once again break the covalent bonds. And as we know, whenever breaking the covalent bond, what will get? We get electron will come pair. And electron they move towards N side and hole they move towards the P side. It means electron in the N side, if they move towards the P side, what happens? This electron they will recombine with the hole. And whenever the electron will recombine, then what happens? Because of recombination, they will get some energy. Because of that energy, you can break the covalent bonds. And whenever that is near to the P or near to the positive terminal, then what happens? Whenever breaking the covalent bonds, what happens? The electron hole come in pairs. That electron they move towards N side and hole they move towards the P side. That is nothing but another way of expressing forward bias. It means what you have to write in the exam. Don't worry this much of detail in the exam. First you write the lead diagram. You write what is forward bias. The positive of the battery and the P terminal connected to the positive battery, N terminal connected to the negative battery. That is enough for forward bias. And second point in forward bias, the holes will be required by the positive battery, electron will be required by the negative battery. They move towards the junction, and because of electron hole they move towards the junction, they reduce the depression layer. They reduce the width of the depression layer. Then third point, because of the reducing depression layer, we are having the more current in the forward bias. Last point, your applied voltage and barrier potential, they are in the opposite direction. The applied voltage opposes the barrier potential. That's why you are getting more current in the forward bias. And important thing, as you know, the barrier potential for germanium 0.3 and for silicon 0.7. We have to apply the external voltage that should be more than 0.3 and 0.7. Then only you are having more current, or then only you can eliminate the depression layer, or you can reduce the depression layer, or indicate narrow depression layer. Then you are having more current in the forward bias. This is about simple way of your understanding about the forward bias. Now we go for another one, that is about your reverse bias. What is the effect of the reverse bias? We go for that. What is the effect of the reverse bias? Only can change the polarity of the, yes, you can change the polarity of the battery. The remaining thing as it is, and here you can take here negative positive. Now we are going for the reverse bias. For the reverse bias. of the reverse bias. Look here, first step what you write, this is your VI. First you write what is reverse bias. No doubt the reverse bias is nothing but the P terminal is connected to the negative battery, N terminal is connected to the positive battery. That is nothing but reverse bias. It means opposite polarity, because we know the whole side positive charge that is connected to the negative, and electrons and negative charge that is connected to the positive. Or you can say opposite polarity reverse bias, same polarity forward bias. It means in the exam what you read, what is reverse bias? The P type semiconductor is connected to the negative battery, and N type semiconductor is connected to the positive battery. This is about the reverse bias. Next step what happens? Look here, as usual, in the holes in the P side, they will be attracted by the negative battery. Electrons from the N side, they will be attracted by the positive battery. No doubt. Now what happens? Like that they are moving. They are moving from the away from the actually, here in the reverse bias, the majority carriers, I am saying the holes in the P type, they are majority carriers. Electrons in the N type, they are majority carriers. I am saying the majority carriers, they are moving away from the junction. They are moving away from the junction. And as I said, the holes will be attracted by the negative battery. Electrons will be attracted by the positive battery. Or I can say the holes will be moving away from the junction. Electrons also moving away from the junction. Then what happens? They will increase the depression here. Because of the electrons and holes, they are moving away from the junction. What happens? The electron and hole, they are moving away from the junction. They are moving away from the junction. Away from the junction. Then what happens? The deflection layer increases. The important thing, the deflection layer increases. Because of the, I am saying the majority carriers, because of the applied voltage, what happens? The electrons and holes, they will be moving away from the junction. If they are moving away from the junction, what happens? The deflection layer increases. The deflection layer is widening. The deflection layer increases. As we know, if the deflection layer increases, you are not having any current. You are not having any majority charge carriers. It means in the reverse bias, you are not having any current because of majority carriers. Because the majority carriers are moving away from the junction. And another important thing, you should look here. Applied voltage and direct voltage, they are in the same direction. Negative positive, negative positive. Important thing in the reverse bias, the applied voltage support the barrier potential. The applied voltage support the barrier potential. That's why the barrier potential also increases. It means the applied voltage support the barrier potential. That's why it happens. It means the majority charge carriers are not moving in the junction. And what is the current in the reverse bias? What type of current is there in the reverse bias? Actually, in the reverse bias, the current is because of the magnetic carriers. The current is because of the magnetic carriers. It means, look here, in the N type, you are having the holes, and in the P type, the electrons. It means in the reverse bias, the current is because of the magnetic carriers. It means in the N type, the holes are magnetic carriers. In the P type, you are the electron magnetic carrier. In the P type, electrons are magnetic carriers. In the N type, the holes are magnetic carriers. It means in the reverse bias, the current is because of magnetic carriers. The current is because of magnetic carriers. It means what? The applied voltage acts for the forward bias for the magnetic carriers. The applied voltage acts for the forward bias for the magnetic carriers. It means in the reverse bias, current is because of magnetic carriers. Magnetic charge carriers. Current is because of magnetic charge carriers. It means don't confuse. In the reverse bias, the current is because of magnetic carriers. Because the majority carriers are moving away from the junction, and they will increase the depression layer. If the depression layer increases, then what happens? You are not having any current. But no doubt, the current is not there for the majority carriers. But the current is there. That current is very, very small current. That current is because of magnetic carriers. It means in the reverse bias, the current is there. That current is because of the magnetic carriers. And as we know, in the N-type semiconductor, we are having the holes are the magnetic carriers, and in the P-type semiconductor, electrons magnetic carriers. It means the holes, and here in the N-type holes, in the P-type electron, they are moving, and they are moving. They will give the current. That current is nothing but the magnetic carriers. That current is nothing but the leakage current. That also called as leakage current. That is also called as leakage current. Leakage current. That is also called as saturation current. Saturation current. Look here, what is saturation current? What is leakage current? They are all same. It means in the reverse bias, the current is because magnetic carriers, and as we know, the magnetic carriers current is because of temperature, not because of supply voltage. In the reverse bias, the current is because of magnetic carriers. That magnetic carriers current is because of temperature. In the magnetic carrier current is because of the temperature. The important thing in the reverse bias, your current is independent of the applied voltage. In the reverse bias, the current is independent of the applied voltage. That current is called the saturation current. It means in the reverse bias, we are having the current. That current is because of magnetic carriers. And magnetic carriers current nothing but that current is because of temperature. And that current is independent of the applied voltage. And that current nothing but the saturation current. What is saturation? They will ask an exam. What is reverse saturation? What is nothing but the reverse saturation current? No doubt, the current because of magnetic carriers and current because of temperature, and that current is independent of the applied voltage. That is something but the reverse saturation current. Or we can say saturation current. Because studying the reverse bias, that is nothing but the reverse saturation current. And another important thing that is said here, the applied voltage supports the barrier potential. Applied voltage support the barrier potential. That's why the barrier potential increases. The barrier potential increases or depression layer increases. Because of the depression layer increases, what happens? The majority carriers are not moving. They are moving away from the junction. Only the current is because of the magnetic carriers. This is about the importance of the reverse bias. This is about the importance of reverse bias. Keep it in mind. In the reverse bias, the current is because of the magnetic carriers. The current is called leakage current. That current is nothing but the saturation current. And actually, if you go in deep means, if you use in the germanium, that current is nearly about in the microamperes. If you consider germanium diode, that is in terms of microamperes. If you consider the silicon, they are having the nanoamperes. They are having the nanoamperes. The current is in terms of nanoamperes in your silicon. If you consider silicon diode, the current is in terms of nanoamperes. If you consider germanium diode, that is nothing but microamperes. I am saying about the reverse bias. It means maybe you have followed. I will say and repeat. First, you are right. What is reverse bias? Reverse bias nothing but we are applying the P-type semiconductor is connected to the negative of battery, and N-type semiconductor connected to the positive battery. First, you are right. What is reverse bias? Reverse bias nothing but P-type semiconductor is connected to the negative of battery. N-type semiconductor is connected to the positive battery. That is nothing but reverse bias. Then, second point, what you are right. Look here in P-type, the holes are majority carriers. N-type electrons majority carrier. It means what happens? This holes will be attracted by the negative battery. This electron will be attracted by the positive battery. It means what? The electrons and holes, they will be moving away from the junction. The electrons and holes, they are moving away from the junction. If the electrons and holes, they are moving away from the junction, it means what? The depression layer increases. The depression layer increases. And also important thing, because here the majority carriers are moving away from the junction, but you are having some magnetic carriers. In N-type, you are having the holes are magnetic carriers. In P-type, the electromagnetic carriers. It means they are moving. And they are moving, important thing, they are moving, and also your applied voltage that acts for the power base for magnetic carriers. No doubt, the applied voltage is attract the position, attract the force and electrons. But this upright voltage that acts for the forward bias for the magnetic carriers. It means the magnetic carriers are easily moving from N to P, P to N. It means in the reverse bias the current is because of magnetic carriers. In the reverse bias the current is because of magnetic carriers, because the magnetic carriers are moving away from the junction. It means in the reverse bias the current is because of magnetic carriers. That current is what leakage current, that current is what the saturation current. It means the important thing why it is called saturation means in the reverse bias we are having the current, that current is independent of the applied voltage. That current only depends on the temperature. That current only depends upon the temperature. That current is what the reverse saturation current. That current is what the reverse saturation current. Right? It means what I am saying here, the important thing is that whenever you apply the voltage, the thing is that if you apply the voltage that supports the barrier potential. If the applied voltage supports the barrier potential, then what happens? The depression layer increases and the majority carriers are moving away from the junction. Only in the diode current is only because of the magnetic carriers. The current is because of only the magnetic carriers. And as you know, that current is nothing but the temperature. That current is nothing but the temperature. It means the magnetic carriers, they are moving because of the applied voltage acts as a forward bias for the magnetic carriers. It means in the reverse bias they are having the current. That current is because of the magnetic charge carriers. That current is also called as leakage current. That current is also called as saturation current. What is saturation current? Nothing but current because of the magnetic carriers and current because of the temperature, and that current is independent of applied voltage. That is nothing but the reverse saturation current. And finally, as I said here, if you are using the germanium diode, their current in the reverse bias is about microamperes. And if you consider the silicon, their reverse current is about nanoamperes. It means I am saying reverse saturation current for germanium diode is microamperes. Reverse saturation current for the silicon is nanoamperes. Reverse saturation current for the silicon nanoamperes. The reverse saturation current for the germanium diode is microamperes. And this is about the importance of your forward and reverse bias. Maybe I said in the beginning what I said, the important thing in the diode, it conducts only one direction. Or I said in the diode it conducts only the forward bias, because in the forward bias the depression layer reduces, and also your electrons and holes will be moving towards the junction. And also as I said, your applied voltage, the opposes the barrier potential. These are the three important reasons. That's why you are in the forward bias are in the more current. What about reverse bias? Why the diode is not conducting reverse bias? Very simple reason. In the reverse bias, as I said, electron and holes, they will be moving away from the junction. Electrons and holes, they are moving away from the junction. It means if, and also I said, the electron and hole will be attracted to the negative battery. Electron attracted to the positive battery and hole attracted to the negative battery. It means the majority carriers, they are moving away from the junction. It means only having the magnetic carriers in the P type and N type, they are moving. If the magnetic carriers move, that current nothing but that current nothing but magnetic carriers current, that current nothing but your leakage current, or is also called as saturation current. It means in the reverse bias you are having the current, that current is because of magnetic carriers. That current nothing but leakage current, that current nothing but the saturation current. And important thing, that current is independent of the applied voltage. In the reverse bias, the current is independent of the applied voltage. And this is about the reverse bias. Another important thing, as we know already, in the forward bias, you are actually this depression layer that acts as a resistance. The depression layer acts as a resistance. It means in the forward bias, you are having very less resistance. That's why that conducts very more. But in reverse bias, your depression layer is wide, it increases. That's why the resistance is very more, and that's why you are having not current in the reverse bias. It means why the diode conducts only forward bias? Because of the low resistance. Because of the low resistance. But in reverse bias, you have the very high resistance. That high resistance, that's why your diode is not conducting in the reverse bias. Why the diode conducts forward bias? Because of the low resistance. And because of low resistance, the depression layer is very reduces, and reverse bias have more resistance. That is nothing but the depression layer increases. It means one another way you can say about deflationary accelerations. The deflationary accelerations, right? This is about the today's class, and maybe in the tomorrow class we'll go for the VI characteristics. If you draw the graph and what is the effect of the voltage and current, you see about the VI characteristics of PN junction type. Thank you.